Okay, so let's take a look at this precept of week 5. We talked about the first exercise is on binary trees and binary search trees. Few things to notice here. I think you have done in-order traversal in class. In the in-order traversal, what we do is we go to the left subtree recursively, and then we process the root, and then we go to the right subtree. So this piece is the in-order traversal. But if you change the root processing to the beginning, it becomes a pre-order traversal. So you do root first, and then you do left, and then you do right. If you change the root processing to the end, then what we do is we do the left subtree, then we do the right subtree, and then we do the root. So that's what we need to keep in mind as we are trying to solve this problem. So let's take a look at the solution to this problem. So for example, let's start with the what are the in-order traversals. So let's talk about some of the traversals here. So in the case of in-order traversal, what we do is, let's do in-order traversal first. So you have to do the left subtree, and then you do the root, and then you do the right subtree. Within this left subtree, you want to do recursively do the left subtree. So we would be, you would be doing A, and then printing D, which is the root, then go to the right subtree, and then do E, because you do left before the root, and F. So the order in the in-order traversal would be A, D, E, F. And then once you process the left tree, then you process the root, which is M. Then you process the right subtree. There's no left node here, so you would be doing, we do left root, so that would be X, and then you go to the right, and then you do left and root. So the order of the in-order traversal will be do A and D, and then E and F and M, and then you do X, and then Y and Z. So that would be the in-order traversal. Now let's talk about the pre-order traversal of this tree. As we discussed, the idea of pre-order traversal is you go to the root first, then you go to the left, and you go to the right. So the order is root, left, right. You do this recursively throughout the tree. So in this case, when we try to process using the pre-order traversal, so we go to the root, so you output M, and then you go to the left subtree where you go to the root first, you output D, and then you go to, once you process the root, you go to the left subtree, there you process the root again. So the first order would be M, D, A. Then once you process the left subtree, you go to the right subtree and you process F. And then you go to the left tree of that, because remember always the root, left, right. So I go to the left, that would be E. Since I processed this entire tree, now I go to the right and process the root of that, which is X. And then there's no left, so I go to the right, I process the root of that, which is Z, and then process the root of that, that's Y. Now let's talk about the post-order traversal. In the post-order traversal, the order is left, right, root. So it's left, right, root. So let's talk about how this would work. So in the post-order traversal, so we go to the left subtree first. When you start from M, but you go to the left subtree, go to the left subtree of that. So now we have A. So you have the left of D, that's the first thing you're going to process in the post-order traversal. Once you process that, when you go to the right subtree, there you're going to process this subtree, but you're processing in the post-order. That means you do left and then right. There's no right, so that's F. So the first three nodes are in the post-order are A, E, F. And then once you're done with that, then you process D. So we process the left subtree, right subtree, now the root. And now you go to the right subtree to process this one. So then in that case, you're going to be going to the left first, but there's no left, so you go to the right. In the right, you go, you process the left, right, root. So it would be Y, there's no right, so it'll be Z. And then you process X and M. So the order of the nodes in the post order are going to be A, E, F, D, Y, Z, X, M. All right, so if you want to make a note of the answers, they are given here. So you can pause the video and make a note of these answers. So let's move on to the next question, which is to draw a binary tree which has the following pre-order traversal. So the only thing you have to satisfy is the pre-order traversal. Now, as you can imagine, there are a lot of trees you can draw to satisfy one pre-order traversal, which is like if you organize the orders, all the nodes to the right, because you always go to the root in the pre-order traversal, then you go to the root, then you go to the root, then you go to the root, and so on. So you go to the root and then you go to left and right. There's no left here, so you keep going to the root, and so you get that. Here you do the same thing. Like this is another one where it's more balanced be a tree. So you go to the root first, and then you go to the B, and then you go to the left of that, and then right. So you do BAC for this pre-order for this one is BAC. So we have Q, we did the Q, we did BAC, and then we do CY. So BAC, and then we do YXZ. So as you can imagine, there can be a lot of different trees that you can actually draw. If you're interested in the mathematics of this, it's what's called the Catalan number, which is you can do a web search on finding the answer to how many binary trees can you draw from a given sequence of integers. The answer to that question is it's called the Catalan number there. Now, so the next question asks, draw a binary tree that satisfies two things, not just the pre-order, but also the in-order. So that binary tree must satisfy both of these things. So you can ask the questions like this. What does pre-order tells us about the root of the binary tree? It tells us that the root is actually the root Q. The first element in the pre-order is the root of the tree. So what does the in-order tells us about the left and right subtrees of that root? So if you take that root Q, now we know that all the elements B and A have to be to the left of a Q because we process the left subtree in the in-order traversal. So therefore this has to be to the left and this has to be to the right. So one idea we have is that given we know the root and then we know the B and A to be to the left, ZZ and XY to the right. And now we try to do this recursively, this idea. So now if you look at BA, let's try to resolve that tree. So the BA tree, if you look at the pre-order, that tells us who is the root of that tree. That's got to be B. And then where's A? Is it to the left or to the right? Well, that's determined by this. So this one says B comes before A in order traversal. So the A has to be to the right. So for example, this is the tree you will see. So A has to be to the right. And then we begin to break down the other things slowly. So in this case, we say, okay, given these, looking at the pre-order, who is the root? C comes first. So C's got to be the root. And the other guys are to the right of C because in order tells us that the right of C contains Z, X, and Y. So the C, X, and Y have to be onto the right. And now we are trying to determine out of Z, X, and Y, which one is the root. So that if you look at C, X, and Y, you find that this group tells us who is the root of that. That's going to be Y. Okay, so the root is going to be Y. And then similarly, you can argue that the other trees are this. So again, I will ask you to pause the video here and make a note of this and then think about how we got that. So let's go over some of the questions, the KD tree questions. So what is KD tree? KD tree is, in this case, our K is going to be 2, so we're looking at 2D points. So the question is, we know we can organize 1D points in a binary search tree, but if you have 2D points, such as these, you can organize them in a 2D tree. So we will have to figure out how the tree and the plane are related. So let's assume that the points A, B, C, D, E, F come in that order. So when they come in, what we're going to do is we're going to build a tree, and then we're also going to show how they divide the plane. So there are two things that are happening. That when a point is inserted, it's also dividing the plane and also determining which way to go. So the way we do this is that, let's think about the first point. First point is 823. So that becomes the root. And so that's inserted here to the beginning. Now, you can think about this as the odd levels and even levels. And if you had the odd level, you bisect the plane with a vertical line. So this means that anything to the right of A in the tree will be here. Anything to the left of A would be in the tree would be here in this region of the coordinate plane. So when the B comes in, what we do is we compare the x coordinates at the odd levels. We compare x coordinate. So we know that 4 is bigger than 2, so we go to the right and insert it there. So we put the point in here, and now we do a bisecting the plane by a horizontal line. Now, there's an important concept now developing as we're going through this. That concept is called the bounding box or bounding rectangle. The idea of the bounding rectangle is that we want to find a rectangle where we can assure that the point is inside that rectangle. For example, for A, it's always going to be the entire plane. So it's minus infinity to plus infinity. But for B, the bounding box would be this. That's the bounding box for B. And because now we know that anything on this side will be on this bounding box, any point here. And then when you insert C, what we do is we compare now y coordinates. So we compare 2 and 5. We compare y coordinates because 5 is bigger than 2. We go to the right. So the C is inserted to the right. We bisect the plane by a vertical line here. All right, so the C is there. Now, what is the bounding box for C? It's going to be this part here. That's the bounding box for C. And now comes the D. When the D comes, first we compare by the x-coordinate of D is 3, so we go to the right of A. They compare by the y-coordinate. Y-coordinate of D is 3, so we go to the right of B. And then we compare by x-coordinate again. Now the x-coordinate is less than 4. And therefore we go to the left and insert D here. So the D is inserted here. So what's the bounding box for D? That's going to be this part here. That's the part. Now we get the E. So when the E comes in, we compare x coordinate 2 and 1 is less than 2. So we go to the left and then we insert E2 there. And the bounding box for E is going to be this one here. Now we go to when you get to the F, again, we do comparisons, first by x, then by y. We go all the way and insert it here. So f is here. Now, one thing that's important is that we compare y coordinates at this level. So we note that the y coordinate, x coordinate at this level, these are the odd levels. So we could compare 4 to 4. We note that it's the same coordinate. So how do we break these ties? We decide to go to the right. So that's important, okay? So we decided our heuristic is to go to the right when there's a break. So the bounding box for F is going to be that part here. All right. So again, let's review the bounding boxes. This is the bounding box for A. And this is the bounding box for B. And this is the bounding box for C. And the bounding box for D. And the bounding box for E. And the bounding box for F. So those are the bounding boxes of the points. So doing 2B, you are asked to list the bounding boxes for each of the rectangles, for each of the points. Now here in the picture, it's easy for us to just identify them. Now from a programming perspective, how would you do that? How would you go about doing it? So from a programming perspective, if you're trying to determine the bounding boxes, there are a few things that are important. Like for example, we inserted A, so we know the bounding box of A is this entire plane. Now, then we go from A to B, and then B is to the right of A. If it's to the right of A, we change the x-min. So think about the points as x-min, y-min. Think about this as x-min, y-min, x-max, y-max. So there are 2 points that determine the rectangle. Now, so because we go to the right, we change the x-min. So what we notice is that we only change one coordinate from the parent. So we change the x-min to the x coordinate of the parent, which is 2. So we did that. Now going from B to C, what we're going to do is we went to the right of B. So we are changing again one coordinate. So which coordinate are we going to change? In this case, we compare the y coordinates. We compare the y coordinates. So the to go to the right, because that's the we had the even levels. So because we compare the y coordinate, we are changing the y min to the y coordinate of x, which is 2. So note that from the parent, which is b, we only change one thing to go to the other side. So by thinking through that, you can see how the answer gets developed. So B's parent is A, and we only change one coordinate because we went to the right. We changed the x min, and we compare y, and we went to the right, so we change y min. And in this case, when you see a D is inserted to the right of C, now we are comparing x coordinate. So we are changing the x max. So it's actually C is to the right. So let me just make sure that that's the case. So C is to the right. So to get to C, we compare the y coordinates. So 2 and 5 to get to C. And so we change the from the parent C, we change only the x max. We change the x max to get there. All right. So so I think the idea here is that you only change one coordinate when you're going from left to the right. So to as a rule, you can remember the following. If you go to the right of a node, and if your comparison is the x comparison, you change x min. If you go to the left of a node, and if your comparison is the x comparison, you change the x max. And if you go to the right of the node and you compare y, and you change y min, and if you go to the left of you compare y coordinates, and you go to the left, you change the y max. So again, I think it might be helpful to look at this and think about that. So for example, going from A to B, we just had to change this point here. So we change the x min, right? And then going to the when you go to the right of that, we change the y min. So this means y min is changed. The y also came out, so y min is changed, and so on. So that's what you got to remember. So there are 4 cases: whether you compare x and go to the left or right, or you compare y and go to the left or right. In all those 4 cases, one of the x min, y min, x max, y max changes. So you may want to write down those rules to determine how that works. Okay, so let's take a look at the part C of this problem. The part C, what we're trying to do is to see if there's a shaded rectangle given, how many points are within this rectangle. Obviously, a naive algorithm would be to go through the entire tree, some traversal algorithm. You take each point and see if it's inside the rectangle. There are methods to check that quickly. So you can touch on all endpoints to see if these points are inside this shaded rectangle. But there's more we can do with the understanding of the bounding box. Now, so one observation you're making is that the shaded rectangle intersect with the entire plane. So therefore, we must consider the point A. So we understand that point A now is inside the rectangle. So we put that into some kind of a queue so we can return an iterable at the end. Now I have some recursive order that I will traverse this tree. Let's suppose I go to the right tree of this. So when I go to B, I look at the bounding box of B, which is this one here. And that box intersects with the shaded rectangle. So it's possible that B or some other people in B, the subtree, can be inside this rectangle. So I check that and I find out B is not there. So I keep going to the right. So the next I look at C. So in the C, I'm going to look at the bounding box of C, which is this one here. Now, the bounding box of C also intersect with this rectangle. Therefore, I must consider C. But if I consider C, it's not inside, so I keep going to the right. Now I look at F. The bounding box of F happens to be this. Notice that the F is in the boundary because we had to break a tie with the C when it comes to the x-coordinate. So, but what we know is that this shaded rectangle does not intersect with that. So that gives us the first opportunity to prune the tree. So that means any F or anything under F will not be considered because there's no point of looking at them because that couldn't be any point here in this bounding box could not be in this shaded rectangle. Now let's look at once I exhausted. So I go to the left because I'm doing right recursion and then go to the left. So I look at the 5, which is, this is, D. Right? If I look at the bounding box of D is this one here. It definitely intersects. So I must consider D and I also find out that D is in fact inside the shaded rectangle. So I'm done with the entire right subtree. Now I go to the left subtree. In the left subtree, I look at E. The bounding box of E intersect with the shaded. So therefore, I must consider this subtree. And then I figured out that E is not there. There's no more things to look at. So that's how the algorithm works. So each step of the algorithm, you must look at the bounding box of the point you're looking at and see if it intersects with the shaded rectangle. If it does, then you consider points and the points below that. Otherwise, you don't. So we find that the order of traversal based on right recursion and then left would be 1, 2, 3, 4. Then you go 5. Then you go to 6. Let's take a look at the nearest neighbor query. How does that work? Now, here's the idea of the nearest neighbor query. Now, typically, if you do sort of a naive algorithm or brute force algorithm, what you would do is give it a point P. You will try to find the distance to all the points in the set, and then you would find out which one is the shortest. So in a brute force algorithm, I would be doing this. I would take the point and find the distance from that point to A, right? And then I would say, okay, that's the champion distance and that's the champion point. And then I go to B. So I can traverse the tree in any order I like. Go to B and say, okay, that's better. So there's a better champion point, so I'll take the B and update that to be the best distance found so far. Now, the pruning concepts come at this point. So again, you can go to the right, go to the left, whatever the recursion allows you to do. The pruning concept comes here, this way. So if you take the look at the bounding box of E, now we find the distance from the point to the bounding box, which is this distance here. Now we find that that distance is obviously looks to be more than the distance we already have. So what that tells us is that there's no way that a point could be here. So, but making the same argument, so what we are saying is, okay, so we find B, and then when we go to C, we look at the bounding box of C, which is this here. But it's possible that there could be a point here, and because we know the distance from P to this bounding box is shorter than the champion distance so far. So it's possible that there could be a point here. But C is not a better point than B. And then we look at the bounding box of D, which is this one here. The distance from P to that box could be smaller or larger. So if it's smaller, then we must consider this box because there could be a point here closer to B that can be a better point. If it's longer, then there's no need to consider this rectangle or all the points in the tree. So that's called pruning. So in this case, you only get one opportunity to prune, which is to prune the entire subtree of E. And because the distance seems to be bigger than the champion distance you found. So that's sort of the nearest concept. So those are two things that you have to implement. Next, we will take a quick look at the assignment. Okay, so let's consider some of the hints for getting started with the KD tree assignment. So in the KD tree assignment, the two things that I want you to pay attention are things like point2D class is implemented and given to you, and rect_hv class is implemented and given to you. So with these, you don't have to implement a lot of things that you need. Like, for example, you can find the distance between 2 points, or you can see if a point is inside a rectangle, or you can see if 2 rectangles intersect. As you remember, when we talked about the nearest, we had to know the distance between a point and a rectangle. When we look at the range search, we had to know whether 2 things intersect, 2 rectangles intersect. So we can look at that branch of the tree. So there are many things that are really important to know. And then your first assignment is to implement this thing, which is point_st value is not known. It's a generic thing, but the key is a point here. So you're putting a point and a value into this symbol table. The container for that symbol table is a red black BST. So we have to implement the method put, method get. How do you put something to a symbol table? How do you get something from a symbol table? How do you check whether something is in the symbol table? How do you get all the points or the keys in the symbol table? Or how do you find the range of points in the symbol table which falls into this rectangle? Or how do you find the points in the symbol table that are closest to this P that's given? So my advice to you is that the first implementation is a brute force implementation. So which means that you use the red black BST data structure, and it has methods such as put, get, contains, and other things, which you can directly use them to build these things here. So you create a red black BST of point2D and value, and you may want to look at the API to understand that. Notice that the red black BST takes 2 things here, a point, you can make it a point and a value, a comparable point and a value. Okay, so the key things here are that you have to be able to do put, get, contains in log_n time, which would be trivial if you use a red black BST. And then you have to be able to do nearest and range in time proportional to n. In this case, what you have to do is to go through the tree by any order traversal and see if each point, and there are n of them, is inside the range of the given rectangle or closest to a given point. So this part should be fairly straightforward, and write it and check it, test it and write some unit test to know that. And then you must do the following. So you must be able to get through writing the point_st class with a red black BST quite fast. We hope it wouldn't take more than an hour or so, and then test it to make sure it's doing the right things. So you write some unit tests. Now in the second part, instead of a red black BST, you want to use a KD tree to do it, or 2D tree to do it. So all these methods get slightly or a bit more complicated. Now you have to understand how to build a 2D KD tree. So when you say put, you're inserting to a KD tree. So the put method needs to have some kind of a private method that will allow you to take a point and figure out where that point is going to go in this tree. The get method, once you have the put method, so I suggest that you write put and get first with the KD tree idea, because you're going left or right, and then test it with some unit test to make sure that your put and the get are doing what they're supposed to do, because that's an important part before you proceed. And then you can put some random points into it and write the contains. Now contain is more like a search. So when you're searching, you can search for a point by following the order you inserted them. So it's the same thing again, changing the X and Y coordinate comparisons and going through it. This is returning the points of the keys of the symbol table. So essentially you have a symbol table where each KD symbol table which is implemented as a KD tree, and then you have key value pairs in that KD tree, and you want to return all the keys. And when you do when you get to the range, I suggest that you do the range first because that might be easier. And then you try to, again, if you build your KD tree correctly, these things should work quite well based on the algorithm we discussed. So the key thing is to build it right. So let's think about some of the things that might be important here. One is that you need some kind of a node. So let me explain to that using something of a picture. So let me try to draw a picture to explain to you how to build this KD tree. So for example, to build a KD tree, you need some kind of a structure. So you need some kind of a node structure. So let's say you build a node, and because you want, let me see whether I can find these. Okay, there it is. Okay, so there's a node, and in the node you must have maybe a point. You need to have a point. And then you also probably need to store the bounding rectangle in there. And you probably also need to store pointers to the left and right subtrees. Notice that there are four things that we consider here, right? So it can be the left or right. So you can be here or you can be here. Or it can be, in the other case, it can be up or down. So you can think that you can have the same pointer. So this child will be either representing someone to the right in the case of X, or someone above in the case of Y. Same thing with this child. This child would be someone to the left in the case of X, or someone below in the case of Y. So you need to think about what data structures you need. What is your node looks like. So you have point, maybe you need to have your bounding rectangle, some 2 points, maybe some other things. So you have to decide how to design that. And it's very important to get that right, because as you go from parent to the child node, remember that the bounding rectangle, we change only one coordinate of the bounding rectangle. So we take the parent bounding rectangle and change it to the child bounding rectangle. By changing one coordinate based on whether you did X comparisons, you went right, you went left, or you did Y comparison, you went right, you went left. So those are some of the advice I can give you. So make sure you get the put and the get right. And you might want to have some way to know that you change levels. So you might have a Boolean variable, for example, to know that. You continually get the Boolean variable from true to false, false to true, as you go down the tree. So that's another way to make sure. Now, when you do recursion in Java, obviously you need to have a private methods to do recursion, and the public methods call that private method. So this public method will call the private method, which does the recursion for you. Now, if you still need more help, you can come to the help session at 2:30 in CS 105. Good luck with the